So we're thinking here about prime numbers and composite numbers, right? And when we have a number that we know is composite, meaning it has more number pairs, factor pairs that you can multiply together to hit your target number, right? We can find their prime factorization by kind of breaking them down. And what's really cool is that every number, no matter the number, is simply just a sort of a series of prime numbers, and very specific prime numbers can be multiplied together to make that number. So to make every composite number, you can multiply a series of prime numbers, special prime numbers together to get that number. So it's almost like its own little prime code, if you will. So what we have here, so in this example, we've got 10, and 10 we know is composite. So we can break 10 down, and we can kind of think about using factor T's if you want. You also can just kind of think about any factor pair that comes to mind aside from 1 and 10, right? 1 and 10 are already implied, and 10 isn't prime. So we don't want to put it in our prime tree, if you will. So we're only putting pairs in here. Our goal, not really our only, but our goal is to get down to only prime numbers. So what times what can get 10? Well, we know that 2 times 5. So the prime factorization, or the special sort of prime string of numbers that you can always multiply together to get 10, is 2 times 5. You could also add 1 in there, but we know 1 is a little bit of a special case. It's not exactly prime. So 25, we can say 25, they gave us a clue. So 5 times what gets us 25? Well, 5 times 5. So we know that 5 times 5 is that special prime string that you can multiply those numbers together to get 25, or to get your target of that composite number. Here we can say, I know that not 2 because it's odd, but 3, add the digits and you'll see. We know that 3 is indeed a factor of 21, and so we can multiply it by 7, its pair. So the prime string is 3 times 7. So if we come over here to a little bit longer one, we have a little bit bigger number. Let's say we pick 72. Well, in a box like this, in a rectangle, you're going to put non-prime numbers. So you'll put composite numbers. Like you'll see 72 itself is in a box because we know it's composite. Only prime numbers can go inside of these circles. So we can go ahead and say 72. Well, I know that it's divisible by 9, so I could do 9. And I could do 9 times what? Well, 8. Whee! So then from here, what we can do is we can say, okay, did we organize it right? Well, let's find out, because it's kind of given to us in the way that this tree is going to develop. When you do it on paper, you could do these in either order, right? Just kind of like the commutative property, if you will. 8 times 9 is the same as 9 times 8, but it's what we do when we break it down here. So 3 times 3 will get us 9, and 3 and 3 are both prime, so they can go in those circular shapes, right? And then we have 8 times what? Well, I could do 4, which is not prime, and 2, which is prime. And then 4 is composite, so it goes in the rectangle, and we can say 2 times 2 is 4. So then the final piece here is you're going to go and you're going to look at each of these things in these circles. So we'll say 3, actually, to be more specific. Technically, you want to start with your smallest primes. So here I would say 2, and I'm just going to check it off as I write it. 2 times 2, check, times 2, check, times 3 times 3. So this is the specific string that no matter which order you really multiply them in, if you went from biggest to smallest or whatever, when you multiply 2 by 2 by 2 by 3 by 3, every time you're going to get 72. So this composite number of 72, its specific prime string is this right here, and it's unique only to the number 72.